All right, hello everyone. This is our USACO class from 9 to 10 p.m. And let's see, today we're going to do January 2022 questions number 1 and 2. Number 1 is called Herdle, a play on the word Wordle, or on the game Wordle. The second one is a slightly trickier question called Non-Transitive Dice. So this is the second to, actually, I would say third to last USACO class. We have two more taught by Sean teacher. He's going to be bringing you through the rest of the, he's going to be bringing you through the rest of the January contest and taking you through the entire December contest, which if you aren't, like if you're planning to come to one of these sessions, you should probably come to that one because that's the most recent one. Like that, it's the one that it contains the problems that have you saw during the December contest. So he's gonna go over them and solve them and stuff. Yeah. So though, yeah. So, but in that case, but in any case, let's begin working on it. All right, and let me copy the link and okay. So yeah, let's begin. Oops. All right, so this is problem one Herdle. It says the cows, something is going on with my cursor, so let me, this is not working. Okay, there we go. My cursor wasn't working for some reason. But anyway, the cows have created a new puzzle called blah, blah, blah. The new puzzle is blah, blah, blah. They make a 3 by 3 grid representing a field on the farm, with each square of the field occupied by a cow of a certain breed. Of course, it's a breed problem. There are only 26 possible breeds. How convenient. Each identified by a different capital letter in the range A through Z. So that means that we might as well be able to translate A through Z into like 0 to 25. That's, yeah. So there is a way to do that very quickly, and I will show you a little bit later. It involves treating characters like integers, basically, and doing math on them. You're actually able to do that. And one is not told about the pattern of breeds in the field. The goal is to figure them out through a series of guesses. So we have a 3 by 3 grid representing a field on the farm, with each square of the field occupied by a cow of a certain breed. So we have a 3 by 3 grid. Okay, so in each guess, the cows blah blah 3 by 3 grid of uppercase letter, indicating a possible way that the field could be filled with cows. Okay, so it says, yeah, they could, yeah. So some of the squares might in the guess might be correct, obviously, because if they enter randomly, there's a small chance that some of them could be correct. Just like if you randomly choose an answer on a test, like if you're doing ACSL theory and you're like, I don't know how to do this problem, and you just choose A through E, you have a 20% chance of getting it right. It's the same thing here. These are highlighted in green to let the cows know that they are correct. All right. So basically, if a cow just happens to be in the exact right location, and like the cow, let's say that there's a breed A, it's actually supposed to be breed A, and the cow of breed A goes into that particular square, it's gonna light up green. So other squares in the guess might be filled with the cow of the right breed, but in the wrong place. Okay. These are highlighted in yellow. Okay, yeah, so basically so let's say that we have a cow. Okay, so actually let me show you this case. I'm gonna do a simple 2 by 2 example. So I think Wordle is a very popular programming thing. Like I saw this in ACSL last year. ACSL finals had like one of these questions. Like I don't know why, but but if we take a look at this, right? Let's say that we have cows of type A, B, C, and D. And then let's say that so this is what our grid is supposed to be like. So we get full points if we have a cow of type A, B, C, and D up here, like up here on our grid. So that would, so if cow A, right, is on the exact location that where they're supposed to be, then they get a, yeah, then it turns nice and green. However, let's say that we're supposed to have a B cow over here, right? So let's say that we put our B in the lower left-hand corner instead of the upper left-hand corner. In our case, that wouldn't exactly work. That wouldn't be in the right location, but at least we would have a B cow here, right? So basically, this square would turn, we would have a yellow square. Let's see, these are highlighted in yellows. They're not very clear about which one is supposed to be highlighted in yellow, and I'm going to be completely honest, I don't really play Wordle, so I don't know which square is supposed to be yellow. But you might ask, okay, is that even important? Because they're not asking you, unlike, you know, the ACSL quest, our ACSL analog of this question, they're not asking you how many, like where the yellow squares are or where the green squares are. They're just asking you, okay, just list the, or just list how many yellow squares are, or, you know, list how many green squares there are. Because it's given the correct answer grid and the grid representing a guess at this answer, please calculate the number of green and yellow highlighted squares. So you could see this is a pretty simple question. If they're in the right location, then we mark it green, so it goes up by 1. But note that you have to be very careful when you do this because there is a subtle bug that you could run into. You might be like, okay, if they're in the right place, I'm going to loop through the cows and figure out which ones are in the right place. And then I'm going to go back and you know, figure out which cows are like congruent. So I might use a map because then I could tell like, oh yeah, these contain all of that, you know, like these contain this and then these are yellow. But the thing is, a square that is green cannot be yellow. I think I told you, I think I talked about that yesterday when we were talking about the cow grouping. You can't have a single square have two colors at the same time. If it's green, it's automatically removed from the running as it's if it's green, then it cannot count as yellow. So that means that for all intents and purposes, this A is no longer a valid contender for yellow. So you just have to be really careful about that because it is very easy to make that mistake. So, okay, so they have, suppose, I guess, and you also have to be considerate of the number, right? Because there could be 3 A's, right? There could be 3 A's in our original grid. Like, right, you could have 3 A's over here, A, and we could have a single A over here. That means that only one of this A would be highlighted green. And then, yeah, this A would be highlighted green and the other A's would kind of wouldn't do anything. On the other hand, oops, I don't know why I erased that. But on the other hand, though, if we had, let's say, 3 A's over here, it's not like all 3 squares would turn yellow. It's that one of them would turn yellow, and then the rest of them would kind of not turn any color. So what we have to do is the idea is very simple here. Like this is actually one of the more, I think, in my opinion, practical questions that USACO gives you. Like most of them are just completely based on like, do you know this algorithm or not? But here there isn't a particular algorithm that works. Like this isn't a permutation or like what do you call it? Like a greedy algorithm. It's just like, can you program this or not? That's very so. I mean, obviously, there's multiple ways that you could do this, and I would highly recommend programming your own method here. But the idea is that first we loop through each of the characters in sequence. So we compare these and we compare these. This is our reference grid, so the one that was the correct orientation, and this is our actual orientation. So you could see we want to compare each character in the sequence in their corresponding positions. So we want to compare both in the upper left hand corner and so on and so forth. Oops, there we go. Let me break that into half so you could see it. And then, so let's say that they are indeed in the same location. So like, let's say that O, you could see this O and this O are in the same location. So this would be marked green, and you would just kind of, it would be no longer in the running for like, for yellows, for yellow characters, right? We would erase that. And then what would happen is that as we go through this, right, we would indicate that yes, there have, otherwise, like if there aren't any characters and if the two characters are different, we don't necessarily know if there is if there's another C, because again, we're on the very first character. So we actually do something, in my opinion, that's pretty clever. So what we do is that we identify the C over here, and then we say, okay, so in the reference grid, there is one C. And then, in the actual grid over here, there are no C's. So I'm going to put A for actual. There are no cows, no C's. And then you could see that, wait a second. So if you think about that, right, none of the letters, none of the C's in any of the grids would be yellow. So that's why, if you think about it, right, we look at the minimum value. Sure, there's one C over here, but it doesn't make it's not really all that important because there are 0 C's in the actual grid. So we write 0. So we just look at the minimum. If we look at this O, right, there are 2 O's in the reference grid, excluding the one that we got rid of because again, it's a green one. On the other hand, there are 0 in the actual grid because there are, there's no other O other than that one that we got rid of. So there is a 0. So this is C and this is O. The last one I'll do is, let's do a W. There's one W in the reference, one W in the actual. Thus, there is one yellow. So you can see again, if you're confused about how to do this and you're like, okay, I don't even know where to start. Don't just try to don't program this in the most obvious way possible. Like, think about the question. Is the question requiring you to indicate where the yellow squares are? If they are, then your program would be different, but they're just asking you what squares are highlighted in green and which ones are in yellow. So yeah, so that's basically how you should be looking at your problem. So figure out what you actually need to solve. Like the problem could say whatever it wants, but it's ultimately the output that matters. You might need to actually follow the instructions in the problem, like actually color the squares in yellow or green for some problems, but in this one, you don't have to. So just be careful, just be cautious about which ones or what parts of the program you actually implement. Like, are you going to actually implement the actual coloring algorithm, or are you just gonna do something a little bit cleverer and not actually count everything? So I'm going to pull, okay, this was the one from yesterday. So let's get started and yeah, let's get started on this. So we will have import java.util. And I just realized I forgot to put up my problems from yesterday. So let me do that. I keep forgetting to do that. Oops, public class Herdle, and then public static void main. Okay, so we have that. And then we will make, of course, a scanner s equals new scanner. So we will now make a 3x3 grid. Yeah, we're going to make a 3x3 grid. And then we'll call this one, we'll make a 2-dimensional array. Actually, do we need to, actually, you know what? I'll make it a little bit simpler and I'll make an array of 3 characters. So we'll make, a string of 3 characters. So string reference equals new string of length, array of length 3, string value equals new string 3, like that. So we could use a multi-dimensional array. You don't have to though. So we will do int I equals 0, I equals 3, I plus plus, reference of I equals s dot next. Oops, we don't need an if. And then we could do the same thing. Instead of reference, we just put value. Nice and simple. So basically, we're gonna loop over the whole thing 2 times. Oh, sorry, we're gonna loop over the whole thing once. We're gonna compare each character against each character. So we're gonna, yeah, basically we make a nested for loop that, that compares each character at the same location. Let me that. So I'm gonna do char ref is going to be reference of I char at j char actual equals value. Or let me do an act. Let me turn this into actual. Actual, because value doesn't actually, it sounds really vague. Char at of j. So okay, so now we check, right? We do if reference, if our target grid equals the one in our actual, then we would indicate that the number of greens goes up. On the other hand, right, we would want to go and see that we would want to add to our list the number of, we would want to indicate that there are 5 C's, or there are 5 D's, or there are 5 E's, or there's 2 D's and 1 E, right? So the way you can do, there are a couple ways you could do this, and actually there is one way where you could use a hash table or a hash map. And actually, I'm thinking about using that right now. I'm trying to think of the simplest method to deal with this. All right, actually, you know what? Let's just use an array for this. So I will make an array corresponding to each of the, so I'm going to make, let's see, reference count, new int 26, one for each letter of the alphabet, and then we'll do the actual count. So here's the so it seems really obvious that we might do something like reference count and then ref plus plus, and then actual count act plus plus. It sounds obvious, but that's actually not the end of the story, because you're like, oh, wait a second. That doesn't really make a lot of sense because this is a char and this is an int array. So shouldn't ints go in here? If you hope, maybe you learned this in class, but for those that haven't, chars are basically ints in another skin, basically. They basically act the same as ints. We call them chars because they're a little bit, they act a little bit different from ints, but for all intents and purposes, a char is basically a number. And it's a number that corresponds to a character. So whenever you write something like this, right, A, you're not writing a character per se, but you're actually writing the number 65, capital A. So this capital A in ASCII actually corresponds to the number 65, and you could imagine that B corresponds to 66. So whenever you might have seen your teachers do like a character and then +1, it works because these all ultimately boils down to numbers. You're just like, they're just simple numbers. So obviously, if we can treat these as numbers, our problem is capital A stands for 65, not 0. So the obvious solution is to subtract the value of capital A. Subtract the value of capital A. So we do minus, and if you do A minus A, obviously you're going to end up with 0. You do B minus A, you're going to end up with 1, like that. So now all we do is we figure out, remember we're looking for the minimum value. So we do for int I equals 0, I is less than 26, I plus plus. We add up the yellows, so int yellows equals 0, and then plus equals math.min, and then actual counts of I, and then we will simply print out green, and then we'll print out yellows. So you could see this is not actually that difficult of a problem. So I'm going to save this to my USACO folder. Okay, and I'm going to submit this to the problem. I'm gonna submit this problem. Okay, I have to log in. Okie dokie. So I've submitted it, and let's see how I'm gonna see how well it works. Okay, so let's see if it worked. Uh-oh. Oh, I forgot to put system dot in. Sorry. I'm submitting it again. I'm just scanning for errors if I made any. Oh, oops. Okay, this was kind of silly. I didn't save the file. Yeah. I tried submitting it again and I didn't save the file. Okay, let's take a look. Okay, I lost my window. I have a bunch of them. Oh my God. Okay. I'm making a lot of typos today. This should be square brackets. But you know what? I will at the end of class, I will check these. I don't want to do it in the middle of class. I just realized how much time I spent on this. Just like checking for errors. So actually, I'm going to do that while I explain the problem. So if you hear me pause, it's because I'm resubmitting the program and I'm checking if it works. Okay, so the next one is called non-transitive dice. So okay, so it says to pass the time in the barn, the cows enjoy playing dice games. So they have dice X and Y. So when both are rolled, then the winner is the one with the higher number showing. Okay, and if both land on the same number, they're re-rolled. Yeah, as long as there continues to be a tie. We say X beats Y if it's more likely then X will win this game than Y. Okay, so here's an interesting thing here. We have die A has the numbers 4, 5, 6, 7. I guess the four-sided dice must look like tetrahedrons. So we have a dice A is equal 4, 5, 6, 7, 2, 4, 5, 10, and then 1, 4, 8, 9. So they have an interesting property. So A beats B, B beats C, and C also beats A. Okay, and it's because none of the three dice are the best at beating the other two. Because there is a case where C beats A, right? C beats A because our 8 is greater than 6, right? And then this is also greater than 7. So, and then all of these numbers are smaller than 8, and all of these numbers are also smaller than 9. Oop, okay. And then let's see, A beats B because we have our 2, 4, and 5 over here. And then let's see, B beats C because you could see that 1, 4, 8 are all smaller than this. And you could see A beats C, or C beats A because these three numbers are smaller. So yeah. So it says at least each die beats one die, but it loses to another die. pretty much. So it says, given the numbers on the face of two four-sided die A and B, please help the cows determine whether there's a way to assign numbers on the face of a third die C so that the set of dice is non-transitive. The numbers on the faces of all dice must be integers in the range 1 through 10 inclusive. Okay, so let's take another look at this. So this is a very tricky question, not because it's hard to program, but because it's just difficult to understand. Yeah, okay. Oh, okay, so we say die X beats die Y if it's more likely that X will win this game than Y. So you could see that in our case, we have 3 cases that both lose to the largest number. And we have 3 cases that both lose to the largest number, and so on and so forth. Yeah, so it is very likely, right? It's 3 out of 4. Actually, in this case, it's 4 out of 4 cases, or you could see it. Yeah, X will win this game than Y because it has this 10. So this 10 will beat out every single one of them, right? This 5 will also beat out the 4 and 5. So you could see our 10 wins in 6 cases or 4 cases. Our 5 wins in 2. And then so you could see we have a little trouble with these because our 7 can only be 2, 4, and 5 and not our 4. Yeah, so hopefully you can see how that works. So just think about it. Just think about how the probabilities work. And then so our input format consists of several independent test cases, all of which need to be solved correctly. I really don't like these kinds of problems. This is a cheap way to get many different kinds of, it's a cheap way to get people. It's like, okay, well, our problem isn't hard enough, so we need to just add more material. It's like, yeah, your teacher is like, oh yeah, my tests aren't hard enough, so I'm going to add more material to them just so people like get more questions wrong. Or so the first line of input contains 10, the number of test cases you need to solve. At least it only goes up to 1 through 10. There's other problems that go up to like 1,000, which is really not a nice move on their part. They have one test case in terms of 8 numbers. So they have the numbers on the 4 sides of dice A, there's numbers on the 4 sides of dice B. So you could see there's 4, 4, and then 4. All numbers are between the range 1 through 10, but not in sorted order. So but you can't really sort these. I mean, you can't just stick this into one array and sort it because remember, this goes into array 1 and this goes into array 2. And sorry, dice A and dice B. So so you could sort, you might be able to get away with sorting these individually, but you cannot sort the whole thing because otherwise everything gets jumbled up. The same number might appear multiple times, even on the same die, blah, blah, blah. Please write T lines of output. Kth line should be yes if it's possible to design a die C to make the kth test case into a set of non-transitive dice, and no otherwise. So remember, so take a look at this. We need to have it so that let me go back up to read it. A beats B, B beats B, B beats C, and C also beats A. So A, oops, I said A and I drew a C. So A, B, C. So A beats B, B beats C, and C beats A. So I'm gonna draw an arrow like that. So how does A beat B? So you just want to make sure that you know how, because you might want to take a look at you might want to take a look at the test case. You might want to, you might want to examine this to make sure why A beats B. So in our case, we have 4, 5. So in our case, this 10 beats all of them easily, right? Right. So we want to basically compare, actually, a slightly simpler method, but now that I thought of it, would be to compare this against each one and see how many wins there are versus how many losses there are, right? So if we rolled this 4, imagine we rolled this 4 and we hypothetically rolled 2, 4, 5, and 10. Who would win? Well, uh, then obviously there'd be two cases where we won, one case where we tied, and then every other case we would lose. So we'd say there is one win and then two ties. Remember, they say we keep re-rolling until we hit when we get out of the tie. So in effect, there are no ties. Five, there are, let's see, there's one win and then two loses. And this is a loss, two losses. So we're looking at from the perspective of dice A, wins and losses, but you could just flip them. Losses become wins, wins become losses for dice B. This five, let's see, we have two wins, one tie, and one loss. Our six has three wins and one loss. And our seven has three wins and one loss. So you could see that our dice loses 5 times, but wins 9 times. You could see dice A beats dice B. So here is the plan. Basically, we will have to make a method that does this calculation for us. Because again, our method was just to test every single possibility. Then this will involve a little permutation. So I'll give you a quick background on permutation algorithms today, a very simple kind. So basically, we will check if A beats B at all, right? So we will, so we will see if A ties with B, like if there's an equal number of wins and losses, then there is no way to make a transitive dice because this A could equal B. But let's explore two cases, right? What if, okay, so if A is greater than B, everything is going as planned, but what if B is greater than A? What if A is less than B? In this case, so does that mean it doesn't work? Not necessarily. It could still be transitive, right? It could be B is greater than A, which is greater than C, and we just flip it like that. They could work like that. Nobody said it has to exactly be in this order. So for the sake of simplicity, though, it would be very difficult to write a program handling both this case and that case. So in our case, we just want to flip it. All right. So basically, afterwards, the simplest way is just to come up with all possibilities of dice to see if C beats A. And then, to see if C beats A. So we come up with all possibilities of dice C. And then we just, and then once we find a valid solution, we exit out of all of our for loops. And then we basically say that, yes, there is a solution. So there's no real difficult computations going on. It's just test if we can even test if A and B tie to begin with. It's important that you make sure they don't tie. Because if they tie, then there is no way to make them transitive. And then afterwards, you go ahead and then you try all possibilities. So this is a fairly standard permutation algorithm. If you have done ACSL in the past contest of the 2021 to 2022 season, you would have seen this problem. You would have seen a form of permutation too. Yeah, so it is something that kind of pops up. So it is I do want to go over it with you today. So I will make a import java.util public class dice, or I'm going to do non-transitive dice. Public static void main string arc. And then scanner, as equals new scanner. I won't forget the system in this time. All right. Let me go colors. Okay. So now we will make, the thing is, I want to make a method that tests if this worked, like if a given dice A beats given dice B. So I will make I will make some arrays. I'll make an array for A. I'll make an A array. Actually, you know what? I don't need to do that. I'll just pass in the arrays by reference. So I will show you what I mean by that. So I will make a int n. It's a number of test cases. So we have s dot next int. So we have for int test equals 0, test is less than n, test plus plus. I call it test instead of I because I'm going to use the I variable frequently inside of this for loop. So I don't want to use it out here and forbid myself from using it inside. So let's see. So I'm gonna have two int arrays, int a equals new int 4, and int b equals new int 4. So for each b. All right, so now we're gonna check if a ties with b. So I'm gonna write the testing method. So basically, again, for each combination of A and B, I want to see if they win or lose. So I'm going to do static in beat. So there's a wrinkle here, right? Usually you think about it as either being a win or a loss situation. And let's say that you walked into it thinking like that. Well, our problem is there's not just a single win or lose situation, right? We could tie. So we need some kind of tri-state variable, right? We need not just a Boolean, which could only hold two states, but we need a tri-state. We need a win, we need a loss, and then we need a tie. So you're like, okay, maybe I could use an int and represent it using like 0, 1, and 2. But if you think about it, right, ours is, if we say dice x beats, if you read the question, it says we say dice x beats y, if it's more likely that x will win this game than y. But basically, if there are more wins by x, right, if x is greater than y, if we rearrange this so it looks like x minus y is greater than 0, then this is a win, right? Win. So you could see this is the same expression. Let's say x equals y. If we rearrange it, we get x minus y equals 0. So this is a tie. Hopefully you can see what I'm scribbling on my screen. If you can't, just let me know, please. Then finally, if x is less than y, then we could rearrange it so that x minus y is less than 0. So this is a loss. So wait a second, both of these have something very similar to them. What if one is positive, one is equal to 0, one is negative? So you could see it's if we just return an integer, we could tell. I will note as an interesting piece of trivia that it is very common in especially in assembly language programming to just subtract numbers to compare them. Yeah, at least in the one that I know the best. There, if you subtract there's a dedicated instruction that subtracts two numbers, and then it finds and then there's other instructions that like check the sign if it's positive, if it's negative, and then basically all of your less thans and greater thans are based on that subtraction. So they subtract and see if the number is greater than 0 or less than 0. And this interesting aside. Yeah, so anyway, so we have int wins equals 0, losses equals 0. So we just try all possibilities. So we start with I equals 0, and this is our outer loop that controls what's going on in the inner loop. So in our inner loop, right, we will cycle the inner loop through the inner loop will contain the index for the B. Inner loop, outer loop will contain the index for the A. So for every single index in A, we start at, like, let's say that I starts at 0. When we have I equals 0, we will loop through all 4 possible values of J, 0, 1, 2, 3. And then we will we will be done with the for loop, and we will return back up to here. We'll do I plus plus, I will now equal 1, and we'll still loop through all 4 possible values of J again. So we will do basically if A is greater than, if A of J is greater than, A of I, because remember AI is our index, it's greater than B of J, and our wins goes up. Otherwise, A of I is less than B of J, then we do losses plus plus. So now remember our simple solution is just to do wins minus losses. So we will check if if A beats B. And remember, if it's a tie, so it's a tie, we will say there is no good solution to this, like we said earlier, and then we will say no. And then we will continue because there's no reason for us to continue on. Otherwise, let's say that if AB result is less than 0, so A loses to B, we will, it's possible for us to write two versions of this algorithm. They're very similar, but in our case, we just want to like, I don't feel like, I don't feel like doing it. So there is a method on the, there is a method on the array called, actually, you know what? Let's just write a simple swapping algorithm. So to swap two values, you make a temporary one. You copy the values from the first one. Temp of I equals A of I. And then so you make a temporary one because you're just about to clobber all of the values in the A array. And then you restore all of the, you restore the contents of the B array from temp. So this is you might as well be writing this. You might have temp equals A, B equals A, sorry, A equals B, and then B equals temp, like that. So you can see that A is squirreled away because here we completely annihilate the value of A. So we will swap here. Okay. So I will make a 4. So now I'm going to make a C array, right? C equals new int 4. We will go from, we will basically try all possible values of C. So we start with the outer one. We cycle through it the slowest. Right, and then we will basically do the same thing again. Here. And then 1. And then you have another nested for loop inside here that will cycle through 2. And then you could see we have yet another nested one in here that cycles through all 4. Number 4. Okay. And then so if right, if C beats A, so if C beats A, and then so you want to make sure they are greater. If C beats A, and actually if C beats A, and beat A, B beats C, there, B beats C. We don't need to check if A beats B because we already know that. We already checked it here. So we already know that A beats B. We know that already. And you don't want to check it here because you're already checking two things. And if you add another one, it'll just increase your workload. So let's see. So we have this. So obviously, if this one, we have a possible solution. So we have system.out.println. Yes. But the thing is, right, there could be many values of C that work for this, right? There could be there could be thousands, or maybe not thousands. There could be like dozens. So what we want to do is we want to do continue, right? But our problem is that in normal Java loops, continue only takes us out of this for loop. On the other hand, we want to go all the way back up here, right? But if you put continue, it just goes up here because Java doesn't know which for loop that you're referring to. So what we do is we label this with a label. So I will just call this outer. If we label it and then we with the label, it's a name and a colon. If we outer, and then you put it's just like it's almost you name it the same way you would name a variable. So no letters, numbers, dollar signs, underscores. You can't start the name with the number, blah blah blah. If you do it, it will Java will say, oh wow, we want this continue to refer to this one. It's a very underutilized trick. I use it a lot personally. Like that's why I'm using it here. Other people use things like variables. So they have like a Boolean variable and then they set it equal to true and then they break out of the loop if they have to. Yeah. So other people don't. But yeah, this is just one way of doing it. So I'm not saying this is the only way. And otherwise, if we get all the way down here, we will have to put system that out. Now, print ln. No, it's only we only get here. Remember, if we don't ever continue outer. So if we don't want to finish the for loop. This iteration. Okay, so does anybody have any questions about this? Okay, so it looks like nobody has any particular questions at this point. So I will be submitting the program. If you, sorry, if you have a question, you can send it to me in the chat as well. Like if you're confused about something or if you don't know how to implement this algorithm. But yeah, while you guys are typing up your questions, I will submit this program real fast. And I will make sure it works and see if there's any bugs that I forgot to get rid of. Yeah, I don't think there are. It didn't show me any errors. Okay, so it looks like this one works pretty well. Okay, so these are our two problems for the day. You could see that these weren't particularly challenging. We did go through a permutation algorithm. One version of a permutation algorithm involves you nesting for loops. So you have like an array. You come up with all possible values by having the first iterating through the first element, and then the second element, and then the third element, and then the fourth element in the same way. And then at the very center is our little core. It's what we're interested in. It's like, how are we going to use these permutations? All right, so this is okay. So we are officially done with the program for today. I will post the code right now so I don't forget. So we have that. Uh-oh. It's telling me I can't deliver this message. Okay. I will upload the things that we did. And yeah. So just as a reminder for all of you, we have another class tomorrow, but it's not going to be taught by me. It's going to be taught by Sean teacher. So he will also teach the Thursday class. So yeah, he's going to teach Thursday's class as well. So just be on the lookout for that. And I'm going to toss all 4 of them into that. Okay, there we go. I tossed all 4, including the ones that we did yesterday. Okay, yeah. So there is that. Does anybody have any questions? Okay, in that case, have a nice week. Good luck. I won't see you again, probably most of you again. I don't think anyone in my class is watching right now in this class. Yeah, I will send the video I will post a video like I did yesterday. Then I will post the video. Yeah, and I think in the video, you could see my annotation bar. So sorry if that's covering up anything. I'm just not very good with the annotation bar. All right, yeah. So if anyone, okay, so everyone, good luck on USACO. Just yeah, just know your algorithms. If you're curious about any, I'd highly suggest looking them up online, like figuring out how to do them. And yeah, I will see you guys later. So good luck, everybody. If you have any questions, you could stick around.